One world completes an entire year in just 11 hours. In the time it takes most people to sleep through the night, this planet has already raced once around its star. That can only mean one thing: it is orbiting unbelievably close. So close that its day side remains locked at roughly 770 degrees Celsius, hot enough to keep its surface in a permanent state of relentless baking. One hemisphere has never experienced night, the other has never experienced daylight, not once in its entire existence. The planet lies just 48 light years from Earth, close enough for our most powerful telescopes to study in remarkable detail, yet far beyond the reach of any spacecraft humanity has ever built. Then came the most surprising discovery of all. In 2026, observations from the James Webb Space Telescope revealed evidence that challenged one of the biggest assumptions astronomers had made about this world. Not because it found something unexpected, but because it found almost nothing at all. No oceans, no changing weather, no sign that this world had managed to protect itself from the relentless punishment of its star. A silent planet, frozen in one direction, burning in the other, a world that may already be dead, a like, a subscribe, whatever feels right. It all helps this channel reach more people who love falling asleep to the sound of the universe. It starts with a planet discovered orbiting a tiny star so closely that one complete year lasts less than half a day. If we could scatter every known planet across a single cosmic shoreline, you would notice something unexpected. The familiar worlds from our own solar system would occupy only a small part of the landscape. Beyond them stretches an astonishing variety of places, shaped by conditions far more extreme than anything we experience around our own sun. Some resemble giant balls of gas, others are built mostly from rock. Many fall somewhere between those familiar categories, carrying solid surfaces that have been profoundly altered by the intense pull of a nearby star. Astronomers call these distant worlds an exoplanet, meaning a planet that travels around a star other than our sun. The name sounds technical, yet the idea is beautifully simple. Every time we discover another star, we naturally begin wondering whether planets accompany it, just as our own sun is surrounded by a family of worlds. Over the past few decades, that growing search has revealed thousands of exoplanets, each adding another chapter to our understanding of how planetary systems can form and evolve. Among the countless stars scattered through the Milky Way, one group deserves special attention. These are red dwarf stars, small stars that shine much more faintly and remain much cooler than our sun. They dominate our galaxy, making up the overwhelming majority of its stellar population. Their gentle glow may seem unremarkable from afar, yet they have become some of the most valuable targets in modern astronomy. We will return to their remarkable behavior later, because their influence reaches far beyond their modest appearance. Their faintness offers an unexpected advantage. Imagine watching a tiny insect pass across the face of a bright spotlight. The movement would be difficult to notice. Replace that spotlight with a much dimmer lamp, and the same crossing becomes easier to detect. A planet passing in front of a smaller, darker star blocks a larger fraction of its light. That slight reduction stands out more clearly, allowing astronomers to identify rocky planets that might otherwise remain hidden against the brilliance of larger stars. Many of these discoveries lie only a few dozen light years from Earth, close enough for detailed study on a cosmic scale. Several occupy regions of the sky marked by familiar constellations, serving as quiet signposts that help astronomers organize the immense map above us. Even across those immense distances, the light reaching our telescopes still carries subtle clues about the worlds that produced it. One discovery began exactly this way. During the year 2018, the National Aeronautics and Space Administration launched a telescope built specifically to search for nearby planets around small stars. It detected an unusually promising signal, one that seemed straightforward at first glance. But understanding what that faint flicker truly represented demanded years of patient observation, along with a far more capable observatory that had not yet begun revealing its extraordinary view of the universe. Across thousands of stars, countless tiny fluctuations pass almost unnoticed. Most mean very little. A few become the beginning of entirely new worlds. During the year 2018, one of those faint changes reached the instruments aboard the National Aeronautics and Space Administration's Transiting Exoplanet Survey satellite, a mission built to search the nearby sky for planets hidden within ordinary starlight. Its method relied on a transit, meaning the brief moment when a planet crosses directly in front of its parent star. From our point of view, as the planet passes, it blocks a very small fraction of the star's light. The change is tiny, yet modern instruments can measure it with astonishing precision. Each repeated dip becomes another clue, allowing astronomers to estimate the planet's size and calculate how long it takes to complete one orbit. One particular pattern stood apart. The repeating signal came from a small red dwarf star known as Lima Hotel Sierra 3844, located about 48 light years from Earth. The distance sounds immense, yet in the scale of our galaxy, it places this system among our relatively nearby neighbors. Every photon collected by the telescope had spent roughly 48 years traveling across interstellar space before reaching the detectors. The measurements pointed toward a rocky planet rather than a giant ball of gas. Its radius appeared to be about 1.3 times that of Earth, placing it within the category astronomers often call a super Earth. That name can easily sound dramatic, although it describes size rather than habitability. It simply refers to a rocky planet, somewhat larger than our own, without suggesting that it is friendlier or more Earth like. Then another calculation transformed the discovery. The interval between successive transits showed that this planet completed one full orbit in only 11 hours. That meant an entire year there passed before half a day had elapsed on Earth. Such a rapid circuit could happen only if the planet traveled extraordinarily close to its star, at a distance far smaller than the orbit of Mercury around our Sun. Gravity dominates such neighborhoods. Every orbit unfolds within an environment flooded by intense radiation and powerful streams of charged particles flowing outward from the nearby star. The planet races through that harsh region again and again, never receiving a meaningful chance to escape its influence. Its path remains astonishingly tight. We could already estimate its size. We could measure its year. We could even infer the closeness of its orbit with remarkable confidence. But another mystery emerged almost immediately. What becomes of a rocky world living under such relentless conditions? Could any atmosphere remain wrapped around its surface after so much exposure? Or would the star have gradually stripped nearly every trace of gas away across immense spans of time? Distance shapes every world. Shift a planet only a little closer to its star, and the entire course of its history can change. For this newly discovered rocky world, that change was profound. Its orbit carried it into a realm where gravity itself began rewriting the rules, creating conditions unlike anything experienced on Earth. Astronomers describe this state as tidal locking, meaning gravity has slowed a planet's rotation until the same side always faces its star. Our own moon offers a familiar example. It continually presents one face toward Earth because gravity gradually synchronized its rotation with its orbit. The process unfolds over immense spans of time, gently draining rotational energy until a stable balance emerges. Around this distant red dwarf star, that balance arrived under far harsher circumstances. The planet circles so closely that gravity completed the process comparatively quickly, leaving one hemisphere turned toward the star without interruption. Sunrise never arrives on the opposite side. Sunset never reaches the illuminated half. Every location belongs to only one of those two destinies. The scale of that orbit is astonishing. The planet travels at roughly 0.6% of the distance separating Earth from the Sunday. That tiny fraction places it almost unimaginably close to its parent star. Even though the star itself shines much less brightly than our Sun, such proximity overwhelms the advantage of its weaker light. The planet remains immersed in an intense environment every moment of every orbit. But light alone is only part of the story. Stars continuously release streams of electrically charged particles known as stellar wind, meaning a steady flow of matter racing outward through surrounding space. Combined with energetic ultraviolet radiation and powerful X rays, those particles can gradually erode the gases surrounding a nearby planet. Molecule by molecule, an atmosphere may begin slipping away into space if gravity cannot retain it. Earth avoids much of this fate because our planet occupies a far gentler orbit around a more distant star. Here, our atmosphere has endured across billions of years, despite constant exposure to the solar wind. This rocky world lives under very different conditions. Every hour spent circling its star exposes it to another cycle of relentless bombardment with little opportunity for recovery. That realization transformed the discovery. Measuring the planet's size and orbit had revealed where it existed. Understanding whether it still possessed an atmosphere became the far greater challenge. After all, an atmosphere cannot usually be photographed directly across 48 light years of space. We cannot simply zoom in and observe air surrounding a distant world. Instead, astronomers needed another approach. They had to search for indirect evidence, reading tiny clues hidden within the planet's behavior rather than its appearance. If any gases still clung to the surface, they would leave subtle signatures behind. If every layer had already vanished, the planet would reveal that absence in equally revealing ways. Across 48 light years, the greatest clue might come from something we could never see directly, yet still measure with extraordinary precision. Looking across interstellar space often means accepting that our eyes alone are no longer enough. Visible light can reveal a planet's presence, its size, and the rhythm of its orbit, yet many of its most important secrets remain hidden. To learn whether this distant rocky world still carried an atmosphere, astronomers shifted their attention away from ordinary light and began studying something every warm object naturally releases: infrared radiation, the invisible heat energy emitted from its surface. Everything with a temperature above absolute zero gives off infrared radiation. The warmer an object becomes, the more strongly it shines at those invisible wavelengths. Even across 48 light years, the planet releases a faint stream of thermal energy into space. That signal is incredibly weak, yet with instruments sensitive enough, scientists can estimate the planet's surface temperature without ever approaching it. But temperature alone cannot answer the larger mystery. A single measurement offers only one moment in the planet's endless journey around its star. Researchers needed to observe how its heat changed throughout an entire orbit. That approach became known as a phase curve, meaning a continuous record of how the planet's brightness varies as different portions of its surface rotate into our line of sight during each complete revolution around its star. As the planet moves, we gradually view changing fractions of its illuminated hemisphere and its permanently dark hemisphere. If warmth spreads efficiently across the globe, those changes remain relatively modest because the entire planet stays closer to a similar temperature. If heat remains trapped on only one side, the difference becomes much larger, producing a far more dramatic rise and fall in infrared brightness. An atmosphere plays the central role in this test. Thick layers of gas act like enormous conveyors, transporting energy through powerful winds and circulation patterns. On Earth, our atmosphere and oceans continually move warmth from one region to another. Temperatures still vary, yet the contrast remains far less severe than it would on an airless world. But remove that atmosphere, and the situation changes completely. The side facing the star absorbs nearly all incoming energy, while the opposite hemisphere receives almost none. With no air available to carry warmth across the surface, the illuminated half grows intensely hot while the far side remains deeply cold. The contrast itself becomes measurable from astonishing distances. In many ways, this method functions like a planetary fingerprint test. Rather than sampling air directly or sending a spacecraft across interstellar space, astronomers compare patterns of heat with carefully tested physical models. Different atmospheric conditions produce different thermal signatures, allowing researchers to narrow the possibilities with remarkable confidence. Years before the James Webb Space Telescope began exploring the universe, another observatory attempted exactly this experiment. The Spitzer Space Telescope turned its infrared vision toward this remarkable planet, becoming the first instrument to search for the thermal fingerprint that might reveal whether any atmosphere still remained around its scorched surface. Long before the James Webb Space Telescope began examining distant rocky planets, another observatory had already been listening for their faint warmth. The National Aeronautics and Space Administration's Spitzer Space Telescope spent nearly 2 decades studying the universe through infrared light, operating from the year 2003 until the year 2020. Instead of focusing on visible starlight, it specialized in detecting heat, making it uniquely suited to investigate worlds that could never be photographed in ordinary detail. During the year 2019, astronomers directed Spitzer toward this remarkable planet for an extended series of observations. Rather than taking a single snapshot, the telescope followed the planet throughout its entire 11-hour orbit. Every measurement added another piece to the developing thermal pattern. By collecting infrared radiation over a complete circuit, researchers hoped to discover whether warmth was spreading across the globe or remaining trapped beneath the relentless glare of its nearby star. The results quickly attracted attention. Spitzer detected an enormous contrast between the hemisphere facing the star and the hemisphere turned away from it. Very little heat appeared to reach the permanently dark side. That finding strongly suggested the planet lacked a substantial atmosphere capable of transporting energy from one hemisphere to the other. Air, if present in meaningful amounts, should have carried at least some warmth across the surface. Instead, the observations pointed toward a world where temperatures changed dramatically from one side to the other. But astronomy rarely accepts the first explanation without careful testing. Another possibility demanded equal attention. Perhaps the planet simply reflected very little incoming light. Astronomers describe this property as albedo, meaning the fraction of light a surface reflects back into space instead of absorbing. A world with very low albedo appears dark because most of the light striking it is absorbed rather than returned outward. If the surface absorbed nearly all incoming energy, the measured temperatures could potentially resemble those expected from an airless planet. Researchers therefore examined whether unusually low reflectivity alone could account for the infrared observations. The evidence showed that the planet reflected only a small fraction of the starlight reaching its surface. That value matched what scientists would expect from extensive fields of dark volcanic rock, much like basalt found across parts of Earth's ocean floor and on the Moon's broad lava plains. It did not resemble bright clouds, reflective ice, or any surface coated with highly reflective material. Those measurements strengthened the growing case for an atmosphere that was either extremely thin or entirely absent. Even so, important uncertainty remained. Spitzer had reached the limits of what its mirror and detectors could resolve for such a small, distant, rocky world. The observations provided compelling hints rather than absolute certainty. Confirming the planet's true condition would require an observatory with far greater sensitivity, a much larger mirror, and infrared instruments capable of measuring details beyond anything available at the time. Scientific progress sometimes arrives through a single instrument that changes what becomes possible. On the 25th of December, during the year 2021, the James Webb Space Telescope began that transformation. After launch, it traveled toward a stable observing location roughly 1 million miles from Earth, that is nearly 1,609,000 kilometers. From there, far beyond our planet's immediate surroundings, it opened an entirely new window onto distant worlds. The observatory differed from every space telescope that came before it in several important ways. Its primary mirror stretched more than twice the diameter of the mirror aboard the Hubble Space Telescope, allowing it to collect far more light. More importantly for this investigation, it was designed to observe infrared radiation with extraordinary sensitivity. That meant it could detect incredibly faint heat signals arriving from rocky planets many light years away, signals that earlier observatories could only glimpse. For worlds like this one, those abilities made all the difference. Large gas giants produce stronger infrared signatures because of their immense size. Small rocky planets are far less generous. They release only delicate traces of heat, nearly overwhelmed by the brilliance of the stars they orbit. Separating those faint planetary signals from overwhelming starlight requires remarkable precision. The James Webb Space Telescope was engineered specifically to achieve exactly that. One instrument aboard the observatory became especially important. It is called the mid-infrared instrument, a detector built to measure infrared wavelengths where planetary heat shines most clearly. Instead of searching primarily for reflected starlight, the mid-infrared instrument studies thermal energy itself, allowing astronomers to map temperatures across distant planetary surfaces with an accuracy that had never before been available for small rocky worlds. Its location also mattered enormously. Space near Earth may appear empty, yet our planet radiates heat, and our atmosphere absorbs and distorts much of the infrared light arriving from the universe. Ground-based observatories must also peer through constantly shifting layers of air that blur delicate signals. Even the warmth of telescope equipment can interfere with sensitive infrared measurements. By operating far from Earth, while remaining protected behind its enormous 5-layer sunshield, the James Webb Space Telescope shields its instruments from unwanted heat, creating conditions cold enough to detect remarkably faint thermal radiation. But technology alone never produces discovery. It provides the opportunity. Scientists must still design careful observations, compare competing explanations, and test every conclusion against the evidence. During the middle years of the 2020s, an international team finally pointed the James Webb Space Telescope toward this scorched, rocky world. Their goal was beautifully straightforward. They wanted to determine whether the earlier hints represented reality, or whether the planet had managed to preserve even the thinnest envelope of gas despite living so extraordinarily close to its star. Years of engineering eventually met years of scientific patience. An international group of researchers, led by Sebastian Zieba and Laura Kreidberg, brought together specialists in planetary atmospheres, infrared astronomy, and data analysis to examine this remarkable world. Their findings were later published in the journal Nature Astronomy, reflecting the level of scrutiny required before such an unusual conclusion could be shared with the wider scientific community. The investigation centered on observations gathered by the mid-infrared instrument aboard the James Webb Space Telescope. Rather than collecting only a brief glimpse of the planet, the team watched it continuously throughout its entire 11-hour orbit. Every stage of that rapid journey mattered. As different regions of the planet rotated into view, the telescope measured subtle changes in infrared radiation, allowing the researchers to assemble a detailed thermal portrait, one observation at a time. This approach demanded exceptional precision. The differences in brightness were extraordinarily small because the planet itself remained tiny compared with its parent star. Even so, every fraction of additional heat carried useful information. By combining many carefully calibrated measurements, the researchers reconstructed how temperatures varied across the planet instead of relying upon broad estimates or simplified models. That distinction proved essential. Estimating only the average temperature would have concealed the very pattern scientists hoped to uncover. Measuring the permanently illuminated hemisphere and the permanently dark hemisphere independently allowed them to determine whether energy was moving from one side to the other. If an atmosphere existed in substantial amounts, its circulation would soften the temperature contrast. If almost no atmosphere remained, the contrast would become unmistakably sharp. The team also searched for another kind of evidence hidden within the incoming infrared light. They examined what astronomers call a featureless spectrum, meaning a distribution of heat or starlight that contains no recognizable chemical fingerprints. Normally, gases such as water vapor, carbon dioxide, or methane absorb and emit light at specific wavelengths, leaving distinctive patterns behind. Those patterns act much like signatures, revealing the presence of particular molecules even across enormous distances. But a featureless spectrum tells its own story. When those familiar fingerprints fail to appear, the absence itself becomes scientifically valuable. Researchers cannot simply dismiss the missing information. Instead, they ask what conditions could erase every detectable trace. Perhaps the atmosphere has vanished almost completely. Perhaps it remains so extremely thin that it produces no measurable signal. Another possibility is that only a very simple gas survives, one that leaves almost no recognizable features within the observed wavelengths. Each explanation carries different implications for the planet's history. The thermal measurements and the spectrum, therefore, had to be interpreted together rather than separately. Only by comparing both sets of evidence could the researchers begin separating competing possibilities, gradually narrowing the range of answers until the planet itself revealed the story written across its scorched surface through nothing more than its faint infrared glow. Numbers sometimes become landscapes. After the research team completed its analysis, one value stood above all the others, transforming an abstract planet into a place with unmistakable physical character. The hemisphere facing its star was far hotter than many astronomers had expected. The measurements showed a surface temperature of roughly 1040 Kelvin, equivalent to about 770 degrees Celsius, or 1417 degrees Fahrenheit. That figure carries enormous meaning. Many common metals begin to soften or melt within that range, depending on their composition. Rocks remain solid, yet they exist under relentless thermal stress. Every grain of dust, every exposed boulder, and every ancient lava plain spends its existence beneath conditions that would rapidly destroy almost every familiar material associated with life on Earth. A useful comparison comes from volcanic eruptions here at home. Fresh lava flowing across Earth's surface commonly reaches temperatures between roughly 700 degrees Celsius or 1,292 degrees Fahrenheit and 1,200 degrees Celsius or 2,192 degrees Fahrenheit. Those eruptions represent brief geological events, lasting days, weeks, or months before the molten rock gradually cools. This distant world tells a very different story. Its illuminated hemisphere exists within that same thermal range every moment of every orbit. There is no cooling after sunset because sunset never arrives. There is no passing season to reduce the heat. Every exposed surface facing the star remains locked beneath an unending flood of energy, maintaining conditions comparable to active lava fields without interruption. Such temperatures immediately eliminate many possibilities. Liquid water cannot remain stable there. Ice cannot survive. Even complex organic molecules, the carbon-based compounds that form the chemical foundation of every known living organism, break apart under such extreme heat. Before we even examine atmospheric evidence, the thermal environment alone tells us that the star-facing hemisphere cannot provide conditions suitable for biology as we understand it. But the consequences extend beyond life. Minerals expand and contract differently under sustained heating, altering the physical behavior of the crust over immense spans of time. Any volatile substances trapped within surface rocks would have escaped long ago. Materials capable of evaporating under these conditions would gradually disappear, leaving behind only those able to endure relentless exposure. The remarkable aspect is not simply the temperature itself. Planets throughout the galaxy can become extremely hot. What distinguishes this world is the permanence of its condition. The measured value does not represent a temporary spike caused by unusual stellar activity. It does not reflect a passing event or an isolated volcanic eruption. It describes the ordinary state of one complete hemisphere, maintained day after day, year after year, across spans of time that likely reach into billions of years. For this world, blazing heat is not an episode. It is the enduring background against which every geological process has unfolded since gravity first locked one face toward its small red star. The opposite hemisphere completed the picture. While the star-facing side glowed with extraordinary intensity, the surface turned away from its star revealed a dramatically different reality. The infrared measurements showed temperatures far below those of the illuminated hemisphere, with almost no evidence that warmth was crossing from one side of the planet to the other. The contrast was sharper than researchers would expect from a world wrapped in a substantial atmosphere. That finding carried enormous scientific weight. Heat naturally moves from warmer regions toward colder ones whenever a material can transport energy. On planets with thick atmospheres, powerful circulation patterns continually carry warmth across the globe. Air rises, cools, sinks, and flows again in repeating cycles. Winds redistribute energy over immense distances, preventing one hemisphere from becoming overwhelmingly hotter, while the opposite side remains deeply cold. But these observations showed almost none of that balancing effect. The day side retained its intense heat. The night side remained remarkably cold. The two hemispheres behaved almost like separate worlds, sharing the same rocky sphere. Their temperatures stayed largely isolated from one another, despite completing an orbit in only 11 hours. That outcome strongly favors one explanation. An atmosphere capable of transporting large amounts of heat simply does not appear to be present. Even a moderately dense layer of gas would soften the contrast by carrying thermal energy beyond the permanent daylight. Instead, the measurements matched what astronomers expect from an exposed rocky surface, directly absorbing stellar radiation on one side while radiating its stored heat back into space on the other. Our own planet offers an illuminating comparison. Earth experiences day and night every 24 hours, yet temperatures rarely swing to the extraordinary extremes expected for a completely airless world. Our atmosphere acts as an enormous reservoir of moving energy. Oceans strengthen that effect even further, storing heat during warmer periods and releasing it gradually after sunset. Together, they reduce differences between daytime and nighttime, while also helping balance temperatures between the equator and the poles. Nothing similar appears to be happening here. Without broad atmospheric circulation, each hemisphere follows its own thermal destiny. The illuminated side absorbs energy almost continuously. The opposite hemisphere loses heat almost continuously. Between them lies an abrupt transition instead of a gradual one, with little evidence that either side significantly influences the other. For the research team, this agreement between observation and theory proved remarkably persuasive. The thermal map, considered alongside the earlier infrared evidence, supported a consistent conclusion. Lima Hotel Sierra 3844b possesses little or no atmosphere capable of transporting heat across its surface. The hottest and coldest regions occupy the same small rocky planet, separated by only a few hours of travel along its orbit. Yet almost nothing bridges the immense thermal divide stretching from one hemisphere to the other. Heat can reveal far more than temperature. Once researchers understood how energy was distributed across the planet, they began asking another question. What kind of material was producing that pattern? Every type of rock absorbs and releases heat in its own way. Every surface reflects starlight differently. By combining those behaviors, astronomers can begin identifying the character of a world they will never touch. The process resembles comparing fingerprints rather than photographs. Scientists measured how much incoming starlight the planet reflected back into space, while also examining how quickly its surface absorbed heat and radiated that energy away. Laboratory studies and observations within our own solar system provide valuable reference points. Different minerals leave distinctive thermal and reflective signatures, allowing researchers to compare an unknown planet with surfaces that have already been studied in detail. The closest match pointed toward basalt. Basalt is a dark volcanic rock formed when molten lava cools and hardens. On Earth, it covers much of the ocean floor, stretching beneath vast expanses of seawater that most people never see. The Moon also preserves enormous basalt plains across its broad dark regions, traditionally called Maria, a Latin word meaning seas, because early observers believed they were ancient bodies of water rather than solidified lava. Basalt possesses characteristics that fit the observations remarkably well. It reflects only a small fraction of incoming light, giving it a dark appearance. It also stores and releases heat in ways consistent with the thermal measurements gathered by the James Webb Space Telescope. The planet's overall brightness and its infrared behavior together suggest a broad landscape dominated by volcanic rock rather than bright minerals, extensive ice deposits, or reflective cloud layers. That conclusion carries another important implication. Basalt does not appear on a planetary surface without volcanic activity. At some stage in the planet's past, molten rock must have risen from beneath the crust, spilled across the landscape, and gradually cooled into extensive lava plains. Those eruptions may have occurred repeatedly, resurfacing large regions and replacing older terrain with younger volcanic deposits. But the evidence does not reveal when those eruptions happened. The lava could have hardened billions of years ago, preserving an ancient chapter of the planet's history. It could also represent comparatively recent resurfacing on geological timescales, produced by volcanic systems that remained active far longer than expected. The available observations cannot yet distinguish between those possibilities with certainty. Researchers continue examining that question because active volcanism would reshape our understanding of the planet's interior. A world may lose its atmosphere while still retaining enough internal heat to power eruptions beneath its crust. Alternatively, the volcanic fields we infer today may simply record a distant era when the interior remained far more energetic than it is now. For now, the surface appears to tell a restrained yet compelling story. We are probably looking at an immense expanse of dark basalt, forged by flowing lava long ago, with its exact age and present activity remaining among the most intriguing unanswered details surrounding this remarkable rocky world. Imagine standing upon that dark volcanic plain for only a single moment. The landscape would appear familiar in shape, yet almost everything you instinctively expect from a planetary surface would be absent. Weather would not greet you, air would not surround you. The ordinary processes that continually reshape Earth would simply never begin. Without an atmosphere, there can be no wind. Wind is nothing more than moving gas, flowing from one region to another as temperatures and pressures change. On this world, there is no substantial blanket of gas available to move at all. Dust cannot be carried across the landscape by invisible currents. Fine particles remain where gravity and occasional impacts leave them, undisturbed by breezes that never form. Clouds are equally impossible. They require water vapor or other volatile compounds suspended within an atmosphere before cooling into tiny droplets or crystals. Here, there is no meaningful reservoir of gas from which clouds could emerge. No moisture gathers overhead, no storms assemble beyond the horizon. The sky remains permanently empty of drifting formations that are so familiar above Earth. Another absence is even more profound. Sound cannot travel through the vacuum surrounding the surface because sound depends upon particles pushing against one another. On Earth, vibrations move through air until they reach our ears. Across this planet's exposed landscape, even a collapsing rock would produce no traveling wave through empty space. The event would occur, yet nothing resembling an audible echo could spread across the terrain. But the lack of atmosphere also changes the passage of geological time. On Earth, wind gradually wears mountains down. Rain cuts valleys into solid rock. Flowing rivers transport sediment across entire continents. Ice fractures cliffs. Oceans grind coastlines into sand. Every landscape around us records an endless contest between construction and erosion. None of those familiar sculptors appear to be present here. Without moving air or falling rain, surface features may remain remarkably well preserved for immense spans of time. Meteorite impacts can still alter the terrain, and changes driven by the planet's interior may still occur. Yet the constant weathering that softens and reshapes Earth's landscapes has little opportunity to operate. That perspective returns us to the basalt identified through the thermal observations. On Earth, fresh lava begins changing almost immediately after it cools. Water enters tiny fractures. Wind carries abrasive dust across its surface. Chemical reactions slowly transform exposed minerals. Over thousands and millions of years, those once molten flows become increasingly altered. This distant world follows a different path. If an ancient eruption spread dark basalt across its surface long ago, much of that hardened rock may still preserve its original form with astonishing fidelity. A lava field that solidified hundreds of millions or even billions of years in the past could still resemble the landscape left behind when the last molten glow finally faded beneath the relentless light of its nearby star. Long before we can decide whether this world lost an atmosphere, we first have to understand the star that has shaped every moment of its existence. Although its parent star belongs to the family known as red dwarfs, that gentle sounding name hides a far more demanding environment than you might expect. These stars shine less brightly than our own sun in visible light, yet their earliest ages can be astonishingly energetic in other parts of the spectrum. During youth, many red dwarf stars release powerful bursts of ultraviolet radiation and X-ray radiation. Those forms of energy carry far more punch than ordinary visible light. They can break apart molecules, heat the upper reaches of an atmosphere, and gradually give gas enough energy to escape a planet's gravity. A process that seems slow on any single day becomes transformative when repeated across millions or even billions of years. But radiation is only part of the story. Stars also produce what astronomers call stellar wind, a continuous stream of electrically charged particles flowing outward from the star in every direction. Unlike the wind you experience on Earth, this stream is not moving air. It is a flow of tiny particles racing through space at tremendous speed. When those particles strike the upper layers of an atmosphere again and again, they can steadily carry material away into space. Distance determines how severe that assault becomes. We already know this planet circles extraordinarily close to its star, completing an orbit in only 11 hours. From such a nearby path, every pulse of radiation and every wave of stellar wind arrives with far greater intensity than planets receive at the comfortable distance separating Earth from the Sunday. There is little opportunity for recovery. The bombardment continues every day, every orbit, every year. If the planet once possessed an atmosphere rich in gases, this relentless exposure could have stripped it away, layer after layer. Lighter molecules would have escaped first, while heavier gases might have lingered longer before yielding to the same persistent forces. Over immense stretches of time, a once substantial atmosphere could gradually thin until almost nothing remained above the rocky surface. Yet another possibility remains entirely consistent with the evidence. The planet may never have developed a thick atmosphere at all. Conditions during its formation could have left it with only a sparse covering of gas, or perhaps almost none from the beginning. If that happened, the star merely preserved an already barren world instead of transforming one. But the observations alone cannot yet distinguish between those histories with complete confidence. We know the destination with increasing clarity. The starting point remains hidden. Whether this scorched planet endured the slow removal of a once protective atmosphere or emerged into the universe almost completely bare, both possibilities continue to stand as active scientific explanations, reminding us that even remarkable measurements can leave the earliest chapters of a world story unwritten. Step back from this single scorched world for a moment, and an even larger pattern begins to appear. The star that governs this planet is far from unusual. In fact, stars like it dominate our galaxy. Current estimates suggest that roughly 70 to 75% of all stars in the Milky Way belong to the red dwarf family. Wherever you imagine yourself traveling through our galactic neighborhood, you are far more likely to encounter one of these modest stars than a larger star like our own Sunday. That simple statistic changes the scale of everything we have discussed. If most stars are red dwarfs, then a tremendous share of all rocky planets must also circle stars of this kind. Many of those worlds probably formed from similar clouds of gas and dust, many likely settled into remarkably close orbits. Across the galaxy, countless small planets may be living under conditions that resemble those we have been examining. Yet red dwarfs also present a remarkable contradiction. Their fuel burns with extraordinary efficiency, allowing them to shine for astonishing lengths of time. While our sun is expected to exhaust its core fuel after roughly 10 billion years, many red dwarfs could continue producing light for trillions of years. Their lifetimes extend so far into the future that none has yet reached the final stages of stellar evolution, since the universe itself is still far younger than that immense span. At first glance, such longevity sounds encouraging. A stable star enduring for trillions of years seems to offer abundant time for planets to cool, chemistry to unfold, and perhaps life to emerge. You might expect these stars to host some of the most enduring habitats anywhere in the galaxy. But longevity alone tells only part of the story. The earliest chapters of a red dwarf's life can be extraordinarily hostile. During those youthful eras, intense ultraviolet radiation, powerful bursts of X-ray radiation, and persistent stellar wind may batter nearby planets without relief. Any atmosphere forming around a closely orbiting rocky world could face relentless erosion before biological processes ever gain a foothold. Time becomes less valuable if the environment is stripped of its protective shield at the very beginning. This possibility has transformed how astronomers evaluate planets around red dwarfs. Instead of asking only whether a planet occupies the proper orbital distance, researchers must also consider whether its atmosphere could survive the long assault from its parent star. A promising location on paper may conceal an entirely different reality when stellar history enters the calculation. That is why this particular world carries importance beyond its own harsh landscape. We are no longer discussing a theoretical prediction built from computer models alone. We have direct measurements of a rocky planet that appears to possess little to no atmosphere after enduring life beside a red dwarf. LHS 3844b stands as an observed example of what prolonged exposure can produce, offering a tangible glimpse into one possible destiny shared by countless rocky worlds scattered throughout our galaxy. A familiar point of reference helps place this extraordinary planet into perspective. Within our own solar system, Mercury already represents one of the harshest rocky worlds we know. It circles closer to the Sun than any other planet, possesses almost no atmosphere, and carries a surface scarred by countless ancient impacts. Its landscape preserves an immense record of cosmic history because almost nothing remains to erase it. Mercury also demonstrates what happens when heat cannot travel efficiently across a planet. During its long daytime, surface temperatures can climb to around 430 degrees Celsius or 806 degrees Fahrenheit. After sunset, The same terrain can plunge toward negative 180 degrees Celsius or negative 292 degrees Fahrenheit. Those dramatic swings occur because there is very little gas above the surface to trap warmth or carry it into darkness. Each region largely faces space on its own. That pattern should sound familiar. We have already seen the same physical principle, shaping the world around LHS 3844b. Measurements indicate that heat remains concentrated on the permanently illuminated hemisphere while the opposite side stays remarkably cold. Without a substantial atmosphere, energy cannot circulate from one hemisphere to the other. The result is a planet divided into entirely different thermal realities. But the similarities only carry us so far. The conditions on LHS 3844b push far beyond anything Mercury experiences. Its dayside reaches approximately 770 degrees Celsius or 1418 degrees Fahrenheit, placing its rocky surface within the temperature range commonly associated with molten lava on Earth. Every exposed rock remains under those conditions continuously, without sunrise, sunset, or seasonal relief. Its orbit is even more astonishing. Mercury requires about 88 days to complete one journey around the Sunday. LHS 3844b finishes an entire orbit in only 11 hours. A complete year on that distant planet passes before a single day has ended for many people on Earth. The planet races around its parent star with astonishing speed while remaining locked in the same orientation throughout every orbit. This comparison helps transform an unfamiliar discovery into something you can picture. Mercury already stands in our minds as a blistering, airless world where survival seems impossible. Now imagine a rocky planet exposed to even greater heat, circling much closer to a smaller star, and completing its entire year in less than half a day. The similarities provide a bridge to understanding, but the differences remind us that LHS 3844b belongs to an entirely separate stellar family, where familiar ideas are carried to far more unforgiving extremes. Imagine standing at a boundary that never moves. On a tidally locked planet, that boundary is known as the terminator line, the narrow region separating the hemisphere locked in permanent daylight from the hemisphere locked in permanent darkness. Since neither side ever rotates into the other's place, this dividing band remains fixed across the surface for the planet's entire existence. It is one of the most intriguing locations planetary scientists consider when evaluating worlds unlike our own. The idea has attracted attention for understandable reasons. If one hemisphere becomes unimaginably hot while the opposite hemisphere remains intensely cold, then the region between them might seem to offer a compromise. Instead of blistering heat or deep cold, temperatures along the terminator line could, in principle, settle somewhere between the two extremes. On some tidally locked planets with substantial atmospheres, researchers have suggested that this narrow strip might provide the most stable environment available across the entire globe. But every planet must be judged according to its own measurements rather than a general possibility. That distinction matters here. We already know this world's dayside reaches temperatures comparable to molten lava, while the observations also indicate almost no atmosphere exists to redistribute heat. Without that protective blanket, the transition between the two hemispheres becomes abrupt instead of gradual. Conditions do not blend smoothly across the surface. They shift dramatically over relatively short distances. Radiation adds another challenge. The planet remains extraordinarily close to its red dwarf star exposing every illuminated region to relentless energy. Even near the terminator line, the combination of intense stellar radiation, lingering surface heat, and the absence of an atmosphere creates an environment that remains profoundly hostile. Current evidence gives no indication that this narrow boundary offers conditions suitable for any known form of life. That conclusion reaches beyond the simple absence of living organisms. When scientists describe a world like LHS 3844b as dead, they are using the word in a much deeper physical sense. The basic chemical processes associated with life require stable environments where complex molecules can persist, liquids can remain available under suitable conditions, and energy can be exchanged without immediately destroying delicate structures. None of those requirements appear to exist anywhere across this planet's exposed surface. But that distinction is important because it reflects evidence rather than imagination. We are not merely observing an empty landscape waiting for future explorers to arrive. The measurements instead describe a world whose surface conditions prevent the familiar chemistry of life from taking hold in the first place. Even the most promising location on the planet, the slender terminator line separating endless daylight from endless darkness, appears unable to provide the ingredients or stability that biology, as we understand it, depends upon. Distance can become strangely abstract until we allow time to carry its meaning. Every detail we have uncovered about this distant planet arrived as light that traveled across space for about 48 years before entering our telescopes. When you picture the world we have been exploring, you are seeing it as it existed decades ago. Nothing reaches us instantly across the galaxy. That realization changes the story. The faint glow analyzed by astronomers began its journey during the late 1970s. While people on Earth lived through those years, built new observatories, launched spacecraft, and gradually learned how to detect distant planets, those same photons crossed the darkness without slowing. They passed between stars until, many decades later, they reached the mirrors of the James Webb Space Telescope, carrying information that had remained untouched throughout the entire voyage. But the separation becomes even more striking when we imagine communication instead of observation. If we somehow transmitted a message moving at the speed of light today, it would still require about 48 years before reaching that planetary system. Any reply, traveling equally fast, would need another 48 years before returning to Earth. Nearly a century would pass before a simple exchange of greetings could ever be completed. Reality moves even more slowly. Our fastest spacecraft travel at only a tiny fraction of the speed of light. At those speeds, crossing 48 light years would require many tens of thousands of years. Civilizations rise and disappear across spans far shorter than such a journey. Languages transform, continents change. The travelers themselves would become part of history long before arriving. For all practical purposes, this planet remains beyond humanity's physical reach with present technology. Yet the remarkable achievement lies elsewhere. We have not depended on imagination alone. We have measured temperatures across opposite hemispheres. We have examined the planet's heat, inferred the character of its surface, and gathered evidence that its atmosphere is almost entirely absent. Every conclusion emerged from real light, completing a real journey across interstellar space. But perhaps that is the deeper wonder. You and I are able to understand a place that will almost certainly remain forever, beyond direct human footsteps. We have transformed faint infrared light into knowledge about volcanic rock, relentless heat, endless darkness, and a world stripped almost bare beneath another star. The planet itself remains unimaginably distant, yet its physical nature has become unexpectedly familiar. Across 48 years of traveling light, the universe has allowed us to measure one more hidden world with extraordinary precision, even if we never stand upon its ancient surface. Sometimes the most revealing discovery arrives as an absence rather than a presence. Earlier, we introduced the idea of a featureless spectrum, a pattern of light that carries almost no recognizable chemical fingerprints. Now we can understand why that seemingly empty result became one of the strongest pieces of evidence in the entire investigation. When the James Webb Space Telescope examined the planet's thermal glow, researchers searched for the unmistakable signatures left by gases such as carbon dioxide, methane, and water vapor. Every gas absorbs and emits specific wavelengths of infrared light, creating distinctive patterns that act much like fingerprints. Those patterns allow astronomers to identify substances they can never touch directly. Yet in this case, those expected fingerprints were essentially absent. But science rarely accepts missing evidence at face value. A weak signal can disappear for several reasons. Perhaps the atmosphere exists, but is extremely thin. Perhaps any remaining gases float too high above the surface or exist in amounts too small for the telescope to distinguish confidently. Instrument sensitivity must always be considered before reaching a conclusion. Careful skepticism comes first. The research team therefore compared multiple lines of evidence instead of relying upon a single measurement. The temperature map already revealed an enormous contrast between the permanent day side and permanent night side. Such an extreme difference indicates that almost no heat travels across the planet. If even a moderately dense atmosphere surrounded the world, circulating gases would move energy from one hemisphere to the other, reducing those dramatic temperature differences. The observed thermal pattern showed almost no sign of that process. But the spectrum supported the same interpretation. No substantial chemical fingerprints appeared where a significant atmosphere should have revealed itself. The heat distribution and the spectral observations pointed toward the same physical explanation from completely different directions. Independent measurements strengthened one another rather than competing. Researchers also tested computer models representing atmospheres with different thicknesses and chemical compositions. Those simulated worlds consistently produced heat patterns or spectral features that differed from the observations. The simplest explanation remained the strongest. Very little gas surrounded the planet, if any remained at all. That conclusion was expressed with careful scientific restraint. The evidence is most consistent with a planet possessing no atmosphere whatsoever, or at most an extremely thin envelope of gas incapable of transporting meaningful amounts of heat from one hemisphere to the other. Such a fragile layer, even if present, would leave the surface exposed to relentless stellar radiation while failing to reshape the world's brutal thermal extremes. In the end, the featureless spectrum did not represent missing information. It became the clearest clue that almost nothing remained above the ancient volcanic ground. Scientific progress does not always arrive through spectacular surprises. Sometimes it advances because uncertainty becomes smaller. A world that confirms the absence of something expected can reshape our understanding just as deeply as one that reveals something entirely new. You and we often celebrate remarkable discoveries, yet dependable certainty can prove even more valuable over time. At first glance, an atmosphere-free planet might seem disappointing. There are no drifting clouds to examine, no chemical mixtures suggesting unfamiliar weather, and no complex layers waiting to be unraveled. But every careful observation adds another reliable piece to a much larger picture. The James Webb Space Telescope did not simply fail to detect an atmosphere. It showed researchers what a genuinely stripped rocky planet looks like when examined with extraordinary precision. That achievement provides what scientists call a calibration point, meaning a dependable reference against which future observations can be compared. Instead of wondering how a bare, rocky planet should appear through the telescope, astronomers now possess a measured example. Its thermal behavior, its nearly featureless spectrum, and its extreme temperature contrast together, establish a standard grounded in observation rather than expectation. But that reference becomes even more valuable when another rocky planet enters the telescope's view. If a different world displays weaker temperature differences between its permanent day side and permanent night side, researchers can compare those measurements against this verified example. If faint chemical fingerprints emerge where none appeared here, they become easier to recognize with greater confidence. Every comparison grows stronger because one endpoint is already understood. This process gradually improves the search for atmospheres throughout our galaxy. Rather than examining every planet in isolation, astronomers can organize discoveries along a spectrum of possibilities. Some worlds may resemble this barren landscape almost exactly. Others may preserve thin gaseous envelopes. A smaller number could reveal thicker atmospheres capable of transporting heat, reshaping climate, and perhaps creating conditions where more complex chemistry becomes possible. But reliable comparisons require trustworthy foundations. A single uncertain observation can introduce confusion across many future studies. A confirmed atmosphere-free planet removes that uncertainty. It anchors the entire field with evidence gathered directly from an actual rocky world instead of depending only upon theoretical models and computer simulations. Viewed this way, this distant planet serves almost like a control experiment for exoplanet atmosphere research. A control experiment provides a known reference so that meaningful differences become easier to recognize elsewhere. Because we now understand how an exposed rocky planet behaves under intense stellar radiation, every future observation gains sharper context. The value of this world, therefore, extends far beyond itself. Its greatest contribution may be helping us recognize, with greater confidence and greater precision, those rare planets where an atmosphere truly survives. A landscape can preserve stories long after the forces that created it have faded. From so far away, we cannot photograph individual mountains, lava plains, or impact craters on this distant world. Instead, we study subtle patterns in the light and heat reflected from its surface, allowing broad geological clues to emerge from remarkably faint signals. One important clue comes from reflectivity, the fraction of incoming starlight that a surface sends back into space. Different materials reflect different amounts of light. A landscape covered by varied rocks, fresh impact scars, and weathered terrain usually produces noticeable differences from one region to another. Researchers therefore search for signs of patchiness that might reveal a complicated geological history. But the observations suggest something more uniform. Across the areas that could be measured, the surface appears to reflect light in a fairly consistent way. That consistency has drawn attention because widespread lava flows can produce extensive sheets of similar volcanic rock. When molten material spreads across a planet before cooling into solid basalt, large regions may end up sharing many of the same physical properties, making the overall surface appear unusually even. The thermal measurements fit into this picture as well. Heat does not emerge from isolated bright regions. that clearly announce active volcanic centers. Instead, the observed infrared signal behaves much more like a broad surface with similar characteristics across the hemisphere that faces its star. That pattern does not prove recent volcanism, but it remains compatible with a world whose visible exterior has been shaped by widespread eruptions sometime during its history. But another explanation remains entirely possible. A relatively smooth appearance does not automatically require fresh lava. If the surface formed long ago and experienced a different history of impacts than expected, or if ancient volcanic plains simply remained largely unchanged afterward, the planet could still display a remarkably uniform signature today. Without detailed images, several geological histories can produce observations that resemble one another. This uncertainty keeps the discussion very much alive. Some planetary scientists see the evidence as a hint that volcanic resurfacing may have occurred on timescales that are geologically recent. Others argue that the existing data do not yet distinguish recent lava flows from an ancient crust that happened to evolve into its present state through different processes. Both interpretations remain scientifically reasonable. For now, the measurements encourage careful restraint instead of bold certainty. We know far more about this world's surface than seemed possible only a few years ago, yet important questions remain unanswered. Future observations with even greater precision may reveal subtle variations hidden within today's data, or perhaps detect new thermal patterns that clarify the planet's geological past. Until then, its rocky exterior continues to offer evidence that is compelling, incomplete, and still waiting to be fully understood. Sometimes a planet loses its atmosphere through a single dramatic event. More often, the process unfolds through several forces working together across immense stretches of time. As we widen our view beyond this particular world, we discover that the galaxy contains many different paths leading to the same destination, a rocky surface left exposed beneath open space. One possibility begins with violent collisions during a planetary system's youth. Giant impacts between developing worlds can blast enormous quantities of gas into space before gravity has a chance to reclaim them. Such collisions also reshape entire planets, melting crusts and altering their future evolution. Even if an atmosphere later forms again, those early encounters may leave it permanently thinner than it otherwise would have been. Gravity also plays an important role. A planet with relatively low mass exerts a weaker gravitational pull, making it more difficult to hold lightweight gases over billions of years. Individual atoms and molecules move at different speeds. Some eventually travel fast enough to escape completely. Given enough time, this gradual leakage can steadily reduce an atmosphere, especially if other forces are helping carry material away. But gravity is only part of the story. A magnetic field, when a planet possesses one, can act as a protective barrier against much of the charged material flowing outward from its parent star. This outward flow is called stellar wind, a continual stream of electrically charged particles moving through space. Around Earth, our magnetic field deflects much of this energetic flow, guiding many particles around the planet instead of allowing them to strike the atmosphere directly. That protection is not perfect, yet it greatly slows atmospheric loss. Even that valuable shield has limits. Bring a rocky world extremely close to an active red dwarf star, and the surrounding environment becomes extraordinarily harsh. Powerful bursts of high-energy radiation combine with an intense stellar wind, continually pressing against any atmosphere that tries to remain in place. Under such relentless conditions, gases escaping into space become increasingly difficult to replace. This is why the circumstances surrounding this planet matter so much. Whatever magnetic field it may once have generated, if one existed at all, would have faced an almost impossible challenge. The planet circles its star at such close range that every protective mechanism must contend with a constant barrage of energy and charged particles. Few atmospheres would be expected to endure for long in such an environment. But perhaps the most striking lesson is how little chance the planet may ever have had. When astronomers consider its orbit together with the behavior of its parent star, the disappearance of an atmosphere begins to resemble the natural consequence of well understood physical laws rather than an extraordinary accident. The barren surface we measure today appears to be the long, predictable result of a world placed in one of the most unforgiving neighborhoods a rocky planet can inhabit. As each new rocky planet comes into focus, we begin to notice that this world is no longer standing alone. It belongs to a steadily growing collection of small planets orbiting dim red dwarf stars, each offering another opportunity to test how these environments shape the worlds around them. Every observation adds another piece to a larger picture that has only recently become clear enough to examine with confidence. Among the most closely watched examples is the remarkable planetary family surrounding the star known as the transiting planets and planetesimals small telescope -1 system. Several of its rocky planets orbit at close distances, making them ideal targets for the James Webb Space Telescope. Researchers have devoted substantial observing time to these worlds because they provide a rare chance to search directly for atmospheres around planets similar in size to Earth. Each successful measurement strengthens our understanding, even when the result is less dramatic than many hoped. Some of these planets remain promising candidates for retaining atmospheres. Others increasingly appear far more exposed. The differences matter enormously. By comparing worlds that formed around the same star under related conditions, astronomers can begin separating the effects of distance, planetary mass, stellar activity, and long-term evolution. Every comparison becomes another carefully controlled experiment conducted by nature itself. But the pattern extends beyond a single planetary family. Additional close orbiting rocky planets discovered around other nearby red dwarf stars are now entering similar observing programs. Each target contributes another measurement of temperature, emitted heat, reflected light, and possible atmospheric gases. These observations remain challenging because the planets are small and faint, yet the James Webb Space Telescope has made studies that once seemed unreachable part of routine scientific investigation. LHS 3844b occupies an especially important place within this growing collection. Unlike a hypothetical model generated inside a computer, it provides direct observational evidence of what a stripped rocky world actually looks like. Its measured thermal contrast, combined with the absence of convincing atmospheric signatures, gives astronomers a reference point against which future discoveries can be compared. That reference grows more valuable every time another similar planet is observed. Patterns carry greater scientific weight than isolated discoveries. A single airless planet might reflect an unusual history or an unlikely sequence of events. Several planets displaying comparable characteristics suggest something much broader at work. Shared outcomes point toward shared physical processes operating across many different planetary systems throughout the galaxy. But that broader perspective is exactly what makes this discovery so influential. We are gradually moving beyond collecting extraordinary individual worlds and toward understanding populations of worlds. With every additional observation, astronomers become better able to recognize which rocky planets survive with atmospheres, which lose them entirely, and how the smallest stars may shape the destinies of countless planets long before any possibility of life can truly begin. The farther we travel across the galaxy, the more often we find ourselves looking back toward home. A distant rocky planet may seem separated from our own history by unimaginable space, yet the physical forces shaping its surface are deeply familiar. They belong to the same set of natural laws that influenced the earliest chapters of our own planetary neighborhood. Long before Earth settled into the comparatively stable world we know today, the inner planets were evolving along very different paths. Mercury formed extremely close to the Sun, where intense radiation and continual streams of energetic particles made it difficult for any substantial atmosphere to survive. Today it remains almost entirely exposed, carrying only an exceedingly thin collection of atoms briefly lifted from its surface before escaping once again into space. Mars tells another part of the same story. Although it formed farther from the Sun, its smaller size gave it less gravity to retain atmospheric gases over immense spans of time. As its internal activity declined, its global magnetic field also faded. Without that broad protective shield, the solar wind gradually stripped away much of the atmosphere that once allowed liquid water to exist across portions of its surface. The transformation unfolded slowly, yet its consequences proved lasting. Venus followed a different path, though atmospheric loss still shaped its history. Evidence suggests that enormous quantities of water may once have existed there. Intense sunlight broke water molecules apart high in the atmosphere, allowing lightweight hydrogen to drift into space, while the remaining chemistry evolved toward the dense carbon dioxide atmosphere surrounding the planet today. Each neighboring world responded differently, yet all were influenced by the balance between gravity, radiation, magnetic protection, and time. But LHS 3844b allows us to examine these same processes while they remain visible in another planetary system. Instead of reconstructing ancient events from scattered clues preserved across nearby planets, we observe a world whose present condition reflects the outcome of atmospheric stripping in remarkably direct ways. Its measured temperatures, exposed rocky surface, and missing atmosphere combine into a living example of forces that also help determine the destinies of worlds orbiting our own star. That connection gives this distant planet an unexpected familiarity. We are not studying an isolated curiosity existing under completely foreign rules. We are watching recognizable planetary physics carried to an even greater extreme. The same mechanisms that influenced Mercury, Mars, and Venus continue operating elsewhere, only under harsher conditions around a smaller, more active star. But perhaps that is the deepest value of discoveries like this one. Across the vast distance separating us, this barren world becomes something like a mirror. Its landscape reflects an amplified version of events that unfolded billions of years ago within our own cosmic backyard, allowing you and me to witness, from afar, a chapter of planetary evolution that shaped the neighbors Earth has known since the beginning. Before we continue following the story of this distant world, it is worth pausing to consider the extraordinary machine that allowed us to know it at all. Every conclusion we have explored depends upon an instrument built to measure warmth so faint that even its own heat would overwhelm the signal if left uncontrolled. The instrument responsible is called the mid-infrared instrument. It observes infrared light, a form of radiation that carries information about temperature rather than visible color. Every object warmer than absolute zero gives off infrared energy. By measuring those tiny emissions with exceptional precision, astronomers can estimate how hot a distant planet becomes as it turns through its orbit. That sounds straightforward. The engineering required is anything but ordinary. To function correctly, the mid-infrared instrument must remain at about negative 266 degrees Celsius or negative 447 degrees Fahrenheit. At warmer temperatures, the instrument itself would glow in infrared light, strongly enough to interfere with the delicate observations it is trying to make. In effect, it would begin seeing its own heat instead of the faint planetary signal arriving from across interstellar space. Keeping the instrument unbelievably cold is therefore not a convenience. It is an absolute necessity. But cooling a telescope in space presents its own challenge. The James Webb Space Telescope travels nearly 1 million miles from Earth, where sunlight still pours across its enormous structure. To protect its sensitive instruments, engineers designed a remarkable 5-layer sunshield stretching across an area roughly the size of a tennis court. Each layer reflects and releases heat before it can pass deeper into the telescope, allowing the protected side to remain extraordinarily cold while the sun continues shining on the opposite side. The difference across that shield is astonishing. One side faces the warmth of direct sunlight, the other shelters scientific instruments operating only a few degrees above absolute zero. Without that carefully engineered barrier, observations like these would become impossible because the telescope's own warmth would overwhelm the faint infrared light arriving from distant planetary systems. Consider what that precision truly means. We are detecting subtle differences in thermal radiation coming from a rocky planet located 48 light years away. The infrared signal reaching the telescope is so weak that even small sources of stray heat within the observatory itself must be carefully controlled. Every layer of insulation, every cooling system, and every carefully planned component exists to preserve those nearly imperceptible photons until they reach the detector. But perhaps the most remarkable achievement is not any single piece of hardware, it is the way every element works together. Through meticulous engineering, humanity has built an observatory capable of transforming unimaginably faint warmth from a distant, airless world into reliable scientific evidence, allowing you and me to understand a place that no spacecraft is ever likely to touch. Across every measurement we have followed, another story has been unfolding beside the planet itself. It is the story of people spread across continents, connected by shared questions rather than shared borders. Astronomers, engineers, data analysts, software specialists, and instrument scientists from multiple universities, research institutes, and space agencies contributed pieces of the work until separate efforts became a single, dependable conclusion. No individual could have completed this investigation alone. Each observation passed through many experienced hands before it became part of the scientific record. Teams examined the telescope, verified its performance, calibrated the instruments, tested computer models, compared independent analyses, and challenged one another's interpretations. Every stage invited scrutiny. Every stage welcomed doubt until the evidence could withstand it. But this discovery did not begin with the James Webb Space Telescope. Years earlier, the Spitzer Space Telescope gathered intriguing hints that this rocky world might lack a substantial atmosphere. Those observations were valuable, yet their precision left room for multiple explanations. A thin atmosphere could still have escaped detection. Instrument limitations also had to be considered. Responsible researchers resisted presenting a dramatic conclusion before stronger evidence became available. That patience shaped everything that followed. When the James Webb Space Telescope finally observed the planet with far greater sensitivity, the earlier findings were not simply accepted, they were tested again. Researchers compared fresh infrared measurements with the older observations, examined whether independent methods reached the same outcome, and explored alternative possibilities that might explain the data. Only after repeated analysis did the separate lines of evidence begin pointing toward the same answer. Science advances this way more often than headlines suggest. New discoveries rarely appear in a single, unforgettable moment. They grow through repetition, correction, discussion, and careful verification. You can imagine each result being placed beside another until the overall picture becomes difficult to dispute. Confidence increases gradually. Certainty is earned. But choosing accuracy over speed demands restraint. Publishing too early risks misleading future research. Waiting allows competing explanations to be examined with equal seriousness before one survives the evidence. In this case, several years separated the earliest indications from the confident conclusion supported by the James Webb Space Telescope. Those years were not lost time, they were part of the discovery itself. That careful approach deserves its own appreciation. Behind every polished scientific paper stand countless unseen hours spent checking calculations, repeating observations, reviewing assumptions, and inviting criticism from other experts before any claim reaches the wider world. The process may appear slow from the outside, yet its deliberate pace is one of its greatest strengths. We often celebrate remarkable telescopes, distant planets, and astonishing discoveries. But those achievements ultimately reflect something deeply human. They reveal a community willing to question its own ideas, wait for stronger evidence, and accept only conclusions that continue standing after every reasonable challenge has been carefully explored. Even after everything we have uncovered, this distant world continues holding back important parts of its story. Every strong conclusion leaves behind a handful of carefully defined uncertainties. Rather than weakening the discovery, those unanswered details give researchers a clearer map of where to look next. We now understand far more than before, yet several fundamental pieces remain beyond today's reach. One enduring question concerns volcanic activity. Has the planet become completely geologically inactive, its interior cooling over immense stretches of time, or could molten rock still rise beneath the surface from time to time? Earlier evidence hinted at a remarkably even surface appearance, yet that observation can support more than one explanation. Fresh lava could have covered older terrain, creating a relatively uniform landscape. An ancient surface, shaped under different conditions, might also appear similar from such great distances. Both possibilities remain scientifically reasonable. But another mystery reaches even further into the planet's past. Did this world once possess a thicker atmosphere before relentless exposure to its nearby star gradually stripped it away? Current observations strongly indicate that almost no atmosphere survives today. They cannot, however, reveal every chapter of the planet's earliest history. If dense gases surrounded the world billions of years ago, much of that evidence may have disappeared long before any telescope observed the system. The composition beneath the visible surface also remains uncertain. Researchers can estimate broad properties from the planet's mass, size, temperature, and emitted heat, yet those measurements cannot identify every mineral hidden below the outer crust. Different combinations of rock and metal could produce similar overall characteristics. Until future observations provide additional clues, several interior models remain consistent with the available evidence. How might these questions eventually be answered? Additional observing time with the James Webb Space Telescope could improve measurement, precision, and reveal subtle details that remain buried within today's data. Longer observing campaigns often reduce uncertainty by collecting more light over extended periods. Future space observatories, designed with even greater sensitivity, may detect signals too faint for current instruments, allowing scientists to investigate rocky worlds with unprecedented detail. But uncertainty should never be mistaken for failure. It marks the boundary between established knowledge and the next discovery. Good science identifies that boundary openly instead of pretending it has already disappeared. Each unanswered question becomes an invitation to test another idea, gather stronger evidence, and refine what we think we know. So, this remarkable planet is unlikely to fade from scientific attention. As telescopes improve and analytical methods become more sophisticated, astronomers will almost certainly return to it again and again. We have measured one of the harshest rocky worlds ever examined in extraordinary detail, yet its remaining mysteries continue offering something equally valuable, a reason to keep looking more carefully into the darkness. As we leave the details of this remarkable world behind, a broader thought begins to emerge. Every planet we study becomes more than an isolated destination. Each one quietly reshapes the larger picture of how often nature creates environments where life might endure. We are no longer looking at a single barren landscape. We are asking what its existence tells us about countless others scattered across the galaxy. The answer is measured rather than dramatic. Thousands of planets beyond our own solar system have now been confirmed, and a very large fraction orbit small, dim stars. Those stars are the most common kind in the Milky Way, making them natural targets for planet searches. Their planets are also easier to detect because they circle close to their stars, completing orbits in relatively short periods that astronomers can observe repeatedly. That success has transformed our understanding of how common rocky worlds truly are. But the same close orbits that help us discover these planets may also expose many of them to relentless conditions. Strong stellar radiation, powerful streams of charged particles, and the effects of tidal locking can combine over immense spans of time. We have now seen one compelling example of where that path may lead. A rocky planet can survive. Its atmosphere may not. That realization encourages caution rather than discouragement. It does not suggest that life is uncommon throughout the universe. It does suggest that some environments once considered promising deserve closer examination before optimistic conclusions are reached. A planet's size alone tells only part of its story. Distance from its star, geological history, magnetic protection, and atmospheric survival all become equally important pieces of the puzzle. Earth appears increasingly fortunate when viewed through this wider lens. Our planet circles at a distance where liquid water can persist, retains a substantial atmosphere, and possesses a magnetic field that helps deflect much of the charged material flowing outward from the sunday. These characteristics may seem ordinary when experienced every day, yet comparisons with other worlds remind us that they cannot be taken for granted. But the search itself becomes richer because of discoveries like this one. Each atmosphere that survives teaches one lesson. Each atmosphere that disappears teaches another. Together, they reveal the range of outcomes nature produces, instead of offering only isolated exceptions. Patterns gradually replace assumptions. So, this distant planet leaves us with perspective more than disappointment. It reminds us that the galaxy contains many paths for rocky worlds to follow, and not all of them resemble Earth's. Some remain welcoming, others become exposed stone beneath an unforgiving sky. Understanding the difference is becoming one of the central goals of modern astronomy, and every carefully measured world brings that understanding into slightly sharper focus. Sometimes, the clearest way to understand our own world is to spend time somewhere entirely different. After tracing the history written across this distant rocky planet, we can return home with new perspective. The comparison is not meant to celebrate Earth as inevitable. It reminds us how many conditions had to unfold together before our own planet became the place you and I know today. Earth occupies a fortunate position around the Sunday. It circles far enough away that the most intense radiation does not constantly batter its atmosphere, yet close enough that sunlight remains strong enough to warm the surface. Our star itself also matters. The Sun is larger and more stable than the small red star surrounding this distant planet, producing a different environment across immense stretches of time. Stability does not remove every danger, but it changes the balance. Another layer of protection surrounds us, without ever becoming visible. Earth's magnetic field extends far into space, forming a broad region where charged particles from the solar wind are redirected around much of the planet. This magnetic shield cannot stop every energetic particle, yet it reduces the continual erosion that would otherwise strip away atmospheric gases far more efficiently. Over billions of years, that protection has mattered enormously. Our atmosphere has also endured. It remained substantial enough to regulate temperatures, transport heat, and support complex chemistry while surviving the steady pressure of the solar wind. Geological activity continuously recycled material between the surface and the interior, while gravity remained strong enough to retain much of the gas surrounding the planet. Each process reinforced the others. Together, they helped preserve conditions that lasted across extraordinary spans of time. But none of these advantages should be mistaken for guarantees. They emerged through a particular sequence of events, extending across about 4.5 billion years. Countless influences shaped that history, from the early formation of Earth's interior to the long evolution of its atmosphere and magnetic field. A different beginning, a different orbit, or a different star could have altered the outcome dramatically. That is why this distant world carries such meaning. It shows us a planetary path where many protective circumstances either never developed or could not survive. The result is a rocky surface exposed directly to an unforgiving stellar environment, holding almost none of the atmospheric blanket that transformed Earth into a living planet. We recognize familiar ingredients, yet they assembled into an entirely different story. Looking across 48 light years, we are not simply observing another planet. We are seeing one possible version of planetary history expressed with remarkable clarity. Under different cosmic circumstances, the place we call home might have followed a similar course. That realization does not diminish Earth's beauty, it deepens it. Our world appears less like the expected outcome of nature and more like a rare balance that endured long enough for us to notice it at all. We arrive once more at the same distant landscape, yet it feels different now. Earlier, we approached it through measurements, observations, and careful evidence. Now we simply remain with the planet itself. Across its dark plains and hardened lava fields, almost nothing appears to interrupt the passage of immense stretches of time. You can imagine standing there as ages drift by, while the horizon scarcely changes at all. The surface may have preserved nearly the same appearance for hundreds of millions or even billions of years. If volcanic activity truly faded long ago, each cooling layer of rock could have remained exposed beneath the star without rain to erode it, flowing water to reshape it, or a substantial atmosphere to carry dust across great distances. Even if isolated geological activity continued beneath the crust, the broad character of the landscape could remain remarkably familiar across intervals that exceed the history of complex life on Earth. But our own planet tells another story. Every day, winds reshape coastlines grain by grain, oceans rise and fall with rhythmic persistence, rivers carve valleys that deepen almost imperceptibly before becoming unmistakable. Deep beneath our feet, immense tectonic plates drift with patient determination, lifting mountains while opening new ocean basins elsewhere. Forests spread, retreat, and return. Ice advances, melts, and advances again. Living creatures continually alter the environments they inhabit, leaving traces that future generations inherit. Nothing truly stands unchanged for long. Even landscapes that appear permanent continue their gradual transformation beneath our notice. The earth you wake upon tomorrow will differ, however slightly, from the one that existed today. Those differences accumulate without pause, weaving together a history that never stops unfolding. But this distant rocky planet reminds us that another kind of planetary existence is possible. A world can reach a stage where change slows almost beyond imagination, where the great cycles that shape familiar landscapes have either ended or become extraordinarily rare. Time continues to pass. The star continues to shine. Yet the surface itself may preserve the same broad face across spans that challenge ordinary human thought. Seen from this perspective, motion becomes precious, weather is precious, flowing water is precious, shifting continents, growing forests, migrating clouds, and living ecosystems all become expressions of a planet that remains profoundly active. We often notice change only when it feels disruptive, yet without continual change, our world would become something entirely different. Looking across the gulf between the stars, we are offered more than a portrait of another planet. We are given a comparison that reshapes our understanding of home. One world rests beneath an almost unchanging sky. The other continues its endless renewal. Between those two histories lies a deeper appreciation of how extraordinary it is that Earth has never stopped becoming something new. Long after our own chapter has passed into history, this distant planet will almost certainly continue its endless path around its small star. Orbit follows orbit with unwavering precision. Seasons never arrive to reshape the landscape. No broad atmosphere rises and falls above the rocks. The same hardened surface faces the passage of immense stretches of time, carrying forward into billions of future years, while almost nothing alters its familiar appearance. It may remain there until another generation of astronomers, equipped with instruments beyond anything we can build today, chooses to look once again. But there is another story woven into that distant orbit. It belongs to us. Across only a few centuries, human curiosity has grown from simple observations of wandering lights into the ability to measure the faint warmth radiating from a rocky world 48 light years away. You and I will never stand beneath its sky or touch its ancient stone, yet careful observation has revealed details that once belonged entirely beyond imagination. We have learned something deeply personal about a place forever beyond our reach. That achievement rests upon countless patient minds working together across many years. Engineers built instruments capable of sensing unimaginably faint infrared light. Scientists tested every assumption against fresh evidence before accepting a conclusion. Observatories separated by decades became part of the same conversation, each adding another piece until uncertainty gradually gave way to confidence. Discovery unfolded through persistence rather than spectacle. Our understanding will continue to change. New telescopes will observe with greater sensitivity. Fresh questions will replace old ones. Some conclusions will become stronger, while others may be refined as better evidence arrives. That steady process does not diminish what we know today. It strengthens it, allowing knowledge to grow through careful correction instead of certainty claimed too soon. But perhaps the deepest lesson has never belonged to this planet alone. By understanding how a world can lose its atmosphere, preserve an ancient surface, and endure beneath relentless starlight, we gain a clearer perspective on the conditions that allowed our own home to remain active across billions of years. Comparison becomes understanding, distance becomes perspective. The universe rarely explains itself through words. Instead, it offers worlds with different histories, different outcomes, and different endings. Each one contributes another sentence to a story much larger than any single planet. As we leave this one behind, it continues its steady journey, unchanged, far beyond ordinary human experience. We return carrying something it cannot possess for itself, the ability to know its history, to place it beside our own, and to recognize that understanding even a lifeless world helps reveal, with greater clarity, the remarkable fortune of living upon one that still continues to change.